Hey, welcome to Lesson 10. This is our last lesson in Chapter 1, so we're moving close to a chapter test. But today we want to finish out our discussion on linear functions with a lesson on modeling. And really what modeling is using mathematics to describe situations that help in the world and solve problems. There's not a single plan that lets you solve every problem. However, there are some guidelines that will definitely help. I'd like to draw your attention here. Reading the problem carefully, it's the first and the essential step. In fact, it's probably the first, second, and third step because experts say that you'll read at least 3 times before you solve a problem. The second step would be to set up variables that represent unknowns. And then thirdly, to write expressions or equations that show how those variables react with each other. So I'd like us to practice this on the word problem that you see here. It says we're choosing between 2 long-distance telephone plans. Plan A has a monthly fee of $15 with a charge of 8 cents per minute for all long-distance calls, while another plan has a monthly fee of $3, so much cheaper in that respect, with a charge of 12 cents per minute for all long-distance calls. So you get lower on the front end, but higher per minute charges. And then the question is, how many minutes of long-distance calls would it require for those 2 plans to cost exactly the same? So as you read this, I hope that you're thinking to yourself, well, there are 2 plans. Let's get some information about them. The first plan is Plan A, and what it says is you start with $15 each month, but then you add to that 8 cents for every call or for every minute of long distance. So if we let X be the number of minutes, because see, the question said how many minutes of long distance. So if the variable stands for minutes, then Plan A could be represented that way. Plan B, well, it's similar, of course. It has a $3 upfront charge, and then the per minute was 12 cents for every long distance minute. The question asks us for how many minutes would it take those 2 plans to be exactly the same. Well, folks, that tells us what we need to do. We want to know when Plan A is equal in cost to Plan B. And we've set up now an equation that shows the relationships between the variables. Now it's up to us to solve it. I'm going to ask you to pause the video, do the arithmetic, and we'll join up here in just a minute. Okay, here's my work. I started out by subtracting 3 from each side so that I could get the number parts together, then 0.08x from each side. I ended up dividing 12 by 0.04 to come up with 300 minutes. The question was a complete sentence. Our answer should also be a complete sentence. So Plan A will cost the same as Plan B. When you've made 300 minutes of long distance calls. There you have it. We came up with a plan, we followed through with the plan. We're going to today explore just several other types of word problems. So here's our next problem. On a certain route or flight, an airline carries 8,000 passengers per month, each of them paying $150. A market survey indicates that for every $1 increase in ticket price, the airline loses 100 passengers. Our job, folks, is to find, bottom line, the ticket price, that's going to be the X in this, for the route that maximizes revenue. Now, as you think about this, we've got a 3-tier plan here to help us answer that question. Let's look at the first tier. Express the number of passengers per month, N, as a function of the ticket price X. Okay, so this is the number of folks on a flight. Well, according to the problem, on average, they would get 8,000 people unless they start raising the price. Every time they raise the price by $1, they lose 100 passengers. So they're going to take away 100 passengers for every dollar that the ticket price is above $150. I want you to think about that for just 1 second. If they start raising the price above $150, for every dollar that it goes above, they're losing 100 passengers from the 8,000 they would expect. Simplifying this function, we're going to end up with 8,000 minus 100x, just distributing across here, plus 150 with 2 more zeros, so that's 15,000. Our net result, the number of ticket purchasers, will be this: 15,000 plus 8,000, that is 23,000, minus 100x, and x is the price of a ticket. All right, let's look at the second bullet point. We're to express monthly revenue for the route, so we're using an R for revenue, as a function of the ticket price. Well, you know and I know that revenue means income, and income means ticket price times the number of tickets sold. The number of tickets sold is what we just had above, n of x. All right, so this gives us a plan to come up with that revenue equation. We're going to multiply ticket price x times the expression that we came up with for the number of passengers on the plane, and that is 23,000 minus 100x. Again, you may or may not want to continue out and distribute. It doesn't matter. It will be correct no matter if you do that or not, but I'm going to just show it here. 23,000x minus 100x squared. Hey, that's not linear, folks. That's quadratic, which is why we will be able to find a maximum value. There will be some top of the hill as far as revenue for this company. Now it says that we're going to use our calculator to find that maximum revenue, so let me get my calculator up. Alright, I've entered in the function into my y equals, and I have experimented until I found a window that fit well. So I want to show you my window settings. X again is the ticket price, and I have my x's going from 0 to 300. Y is revenue, and they are going to make a lot of money, folks. Somewhere less than $1.5 million. Again, I fiddled around with this until I found a window that showed what I wanted, and here it is. What we're asked to find is the maximum ticket price. Ladies and gentlemen, you'll remember from our very first lesson, maximum is one of the maximum is one of the second and trace functions. Second trace, in fact, it's number 4, so let's go down to number 4. Setting a left boundary, so I need to cursor until I'm left of the top of this hill and hit enter. Now set a right boundary, cursor back right and enter, and then enter one more time. According to this, maximum revenue of $1,322,500. They didn't ask us about that, but we can get that. That's the max revenue. Occurs when tickets are $115. All right, let's look at our next problem. A machine produces open boxes using rectangular sheets of metal measuring 15 by 8 inches. The machine cuts equal-sized squares from each corner. Then it shapes the metal into an open box with no cover by turning or folding up the sides. I know I'm going to want to see a picture of that. So 15 by 8. This side is 8 long, this side is 15 long. And this business about squares at the corner. Equal size squares cut from each corner. Okay, so that's a square, same, that's a square, that's a square, that's a square. And if you think about it, they're going to fold up the edges, so that's a fold line, and so is that, etc. Okay. Express the volume of the box in cubic inches as a function of the length of the side of the square cut from each corner, x. So x is that right there and that right there, and following all the way around, all of these have a value of x. Alright, I like that. Volume in this box, let's see, volume is length times width times height, and we're folding up. I know one thing, I know the height of this is going to be whatever x is, because that's the distance that you're folding up. So I know that's going to be x. The length of it, well, that's this side, 15, but it has two cuts out of it that are x long. So length is 15 minus 2x. Width, well, that's 8, and it also has two x parts cut out of it. And then the height of this box, as we said, is going to be x high after you use those things as folds. I'm satisfied with that equation. I see it's got 1, 2, 3 factors of x in it, so this is going to be a cubic. It says we should find the domain and range of the volume. It never asks us to find like the maximum height of x. It's just saying what's the domain and range. And folks, really what this wants us to do is use our head a little bit. Okay, if this side 8 long, how far would they cut before there was no side anymore? That is, what's the maximum that x could be? Well, yeah, it can't be any more than 4. So the domain here, yeah, it kind of makes sense. The domain, folks, would consist of any value of x such that, well, x has to be in between 0 and 4. It can't be 0 because then you wouldn't have a box. It can't be 4 because, again, you wouldn't have a box. So the domain for this thing is between 0 and 4. The range of volumes then, well, you can find that. You can do that just by putting a 4 in for x. If you think about it, this would be y. If you had a cut of 0, then you'd have a volume of 0. If you had a cut that was 0 inches long, then you'd have, let's see, 15 by 8. You know that can't be 0. It could be just a little bit more. So technically, the highest volume that you could get would be 15 times 8, and 15 times 8 is 120. That means that our range is somewhere between 0 and 120 cubic inches. Okay, interesting problem. Drawing helps. Let's look at our last one. We have another geometry problem. You can tell I like geometry. You have 200 feet of fencing to enclose a rectangular garden. Express the area of the garden, A, as a function of one of its dimensions, x. Okay, so let's get a garden pictured here, a rectangle, because it said rectangular garden. We have 200 feet of fencing. So the distance around here is 200. That's the best it can be. One of the sides in this thing is x. Well, that means this one is x as well. And if you think about that 200 feet of fencing, this would have to be 200 minus 2x but cut in half because there are two sides that need that. And just doing the arithmetic there, that makes this 100 minus x. So now we have an expression for each side, and we are supposed to come up with the area of the garden. Area in a rectangle is length times width, or x times, in this case, 100 minus x. We are to find the lengths of the side of a garden with maximum area. Again, you could turn to your calculator or use what you know about geometry. I'm going to go to the calculator. I've entered my equation into the y equals. I experimented again until I found a window that worked, and this is the window I am using. I got that by experimenting again. I looked at the graph and I'm asked to find the length of the sides of the garden that has the maximum area. So second trace and max. And ooh, I think I'm right on it. But I'm gonna get left of center, right of center, and enter. And this says that the maximum area is 2,500, and that would be square feet, when sides are 50 feet long. Good. We've just given you 3 types of problems that we'll be asked to solve. We'll see some that look like these in tomorrow's class. So get out there, do the U-Try. We'll see you in class.